We're with Atul, who's the VP of IoT products at Syntiant, and he's going to talk about how to develop an IMU-based application on the Syntiant NDP 101 TinyML board. So Atul, you can go ahead.
Yeah, thanks, Ariel. So we actually launched the Syntiant's TinyML board about a year ago, exactly in this conference, Imagine conference. And since then, there is a lot of projects people have started. And this has both audio as well as IMU capability. And earlier, we only demonstrated how you can use only audio part. But now today, we would show that how you can also use the sensor application. And so let's get started. So in this presentation, first, we will talk about what is expectation, what we might have already done. Then we would actually start with cloning the project and then go through a smaller presentation, not going through in every detail because you have already completed a project using microphone by now. So we would just highlight only the key differences and where you should be careful. And then I will actually show how would you test the board, and then how would you say that something is working or not working. So let's get started with the prerequisite. So, of course, for this workshop, you need a TinyML board because that's the board we would be using. You need a USB cable to connect it. It's optional to use to have a micro SD card and Arduino IDE, even though when you would collect more data, you would want to actually save the data directly on the micro SD card. And then with the Arduino IDE, you can actually format the data however you like. So these two things are kind of optional for getting started. But when you really want to complete the project, you would need these. And of course, you need to have a Edge Impulse Studio account. And what we would see today works on the free version as well. And then the last one, which is kind of the most important one, is that you have actually completed this tutorial. So we have some difficulty right now to go back and forth between two applications. So I would actually go through all this material later. First, I would just go through the slides. So with this link, this particular link actually takes you to the homepage of TinyML board, where you can actually see what are the features, and then there is a tutorial. And in the tutorial, you would also see the block diagram and things like that. And that tutorial actually takes you through the audio application, which is an application we would recognize go and stop keywords. So once you have completed that, most of the steps are very similar because it is using the same kind of studio. And then you would start going into changing things, which I'm going to talk about next. So let's get started. So for convenience, we actually have made this project, which we call it a circular motion project. And I'll talk about why we actually chose this project. So this, all the data or very small set of data actually is there. And then the whole project is completed. And then you can clone it, and then you get started on something which is already working. You give it a try, and then you would want to improve it. So here is a link. Of course, when you get this presentation, you can actually use this link, or you can actually type in this address, and that takes you to the project. And then it would be asking if you have sign up for free or you already have an account. Since you have already completed the audio project, you would have an account. So follow it as all the steps would be asking you to do. So let's talk about what kind of application we want to develop. So we chose this circular motion. And the reason why we chose circular motion, because it doesn't actually solve any purpose. And this is kind of strictly for demonstration. We chose a project so that does not interfere with our other customers' kind of projects. And this way we can talk about it and we can share the data openly. And it does not interfere with anybody's business in that matter, right? So what we are doing, actually, we would be holding the board and then we would be moving it in a circular motion, and while keeping it on a surface. We call it circular motion, and if you don't want to do the circular motion, then either you keep it steady, or you can actually flip it around, or you can move it into zigzag motion, and that's how you would know that this is an open set. So we're going to talk a little bit more about open set and how we would test it, how the data is captured. One of the key reason why about this circular motion, because as compared to a gesture, which actually has a start and a stop, you actually have to do that many iterations to capture the data. For example, if you have, let's say, a wave, so you actually have to wave 5,000 times, because generally requires like a 2,000 to 5,000 kind of tensors for training. Whereas if you move something in a circular motion, and then when you make the tensors and you have very small window to keep taking the data from, you can actually generate a lot of data from very small amount of work. So that's kind of a good thing about this application. So we can generate the data easily, and then you can test it as well. You don't have to go outside, you have to do something difficult. Anybody can do it, and all you need to do is to take the device and move in a circular motion on a table. So that's kind of the definition of the project, and let's see how we would go about doing it. So when you're cloning the project, it might take 5 to 10 minutes. This is actually one of the project with the least amount of data, so it should not take a lot of time to download the data. And when you see the clone succeeded, then you have a copy, and that's pretty much ready to go. One thing I did find that sometimes main menu does not show up in Edgeimpulse website, especially it depends on your screen size and the resolution. So you may see 3 lines over here, and if you click on there, you would actually see this menu. And we would be going back and forth on this menu as we are actually moving forward. So this clone project already shows all these things like a checked green, which means that these steps have already been completed. So you can actually go and directly deploy it, and you can give it a try. And then you can go back and then you undo some of these steps, so that you would get a feel how would you actually go when you are starting your own complete projects from scratch. And most of these steps are very similar, as we talked about in this TinyML Board tutorial, which is for go and stop. So there is no need to mention the same steps again in this workshop. Are there any questions? Maybe we can take a time and then answer some of the questions.
Yeah, we have actually one question from Justin asking if you have like any recommendations on hardware to connect to Wi-Fi or BLE.
So if you want to connect motion sensor, people have connected to Wi-Fi. I can actually give you, actually if you follow our forum and then you ask the same question, I know that there is a project done for AI for good. So hopefully they can actually share the complete project and how it can be connected. So yes, the board has been connected to other wireless modules.
Yeah, do you remember which one it was, or it's like?
I would hesitate right now before talking to the person who actually completed the project. So once I get their blessing only, then I would rather share the project.
Sounds good. Thank you, Atul.
Thanks. Looks like there's another question.
No, it was just Justin saying thank you.
Okay, good. Okay, so let me move on to next slide. So tensors are kind of the very basic element which goes into neural networks. And for different projects, there may be reasons to change it. So Go and Stop project actually works with 1600 inputs. And 1600 is a good number, but unfortunately, you cannot divide it by 6. So I'm just doing the quick math, and yes, you cannot divide 1600 by 6. So why do we need to divide it by 6? The issue here is that when you're collecting the data from IMU, you're not only going to get only one stream of data. Generally, you would get 3 axes of X, Y, Z accelerometer and 3 axis X, Y, Z gyro. So you get 6 streams of data. And then there is a limitation in the neural processor that it like to see tensors being divisible by 4. So we have to choose the size of the window such that these kind of conditions are met. So here we have chosen 1800 millisecond window, and later on we would show that how this window is reasonable from the different limitations we might have. Now, window size is another parameter which you have to choose, and we have chosen 60 millisecond. So why did we choose 60 millisecond? Because in the project we are going to show, we are actually having inferences done at every 60 millisecond. So if we capture the data and we choose this window increase size to 60 millisecond, essentially what we are doing is that if you're taking, let's say, a minute or 2 minutes of data, and then we just chop one small portion of it, which is one tensor, and then next tensor is generated by sliding the window by 60 millisecond, and we get another tensor. And this way, 1 minute of data can generate probably 1,000 tensors. We could choose something else, because somebody may argue that all these ones, when you are having a small increments, the data may be correlated. So does it make sense to have a small increase? And I would recommend that, yeah, it is a good, it's okay to have this even though data is correlated, because when it comes to evaluation, inferences are done on tensor by tensor basis anyways. Then moving forward, 100 hertz sampling rate is kind of fixed in the TinyML board. So we don't want anybody be changing this, because most of the firmware is kind of actually expecting 100 hertz. So just leave sampling rate to be 100 hertz. If your application requires a different sampling rate, etc., then we really have to kind of engage and then figure it out how to make it happen for you. But by default, let's stick with the 100 hertz of a sampling rate. And the last choice you have, should you pad the data or not with the 0 values? And in my personal opinion, we should not actually 0 pad, because what it does, it artificially makes the complete tensor by having a zeros, whereas in real life you would never get those real zeros. So in some sense, you are actually tricking your training set, and later on it would not work as you expected. So it would be good to not check it. And good thing here is that we are actually taking several minutes of individual streams as a capture data. So this is actually would not apply here. And that's what I would recommend people to take longer sequences and not rely on padding the data. So the next step is when you are designing the impulse. By just the data, you would actually see that, so now the next step actually is to create the project, and IMU has to be selected with the add a processing block. And later on, we would actually delete the block and then we add it to see what we need to do here. So while you're doing it, you have to actually select IMU with the Syntiant in its bracket, because that guides that how this board would be working. And based on your collected data, X, Y, Z, these values actually are taken from the data. So these values would get populated. And my recommendation is to actually leave all of these checked, because first of all, you don't really know that which axis of data would be really important or not. And that's kind of the whole point of machine learning, is that we don't have to analyze all of these data on our own. So leave all of these axes checked. Okay. Now, next step is generally add a processing block. And in this case, you would add a classification keras. And you would notice that the Syntiant IMU is already checked. So as we are proceeding, we have to make sure that the right blocks are chosen. So as I talked earlier, that we have only two classifiers in this application. One is a circular motion and the other one is open set. So here actually I have labeled one of the data set as circle clockwise. And I did it for a purpose. Circular motion could be clockwise or could be counterclockwise. And generally, you don't expect from a neural network to make a decision for you, because it wouldn't know whether you are really interested in a circular or when you say circular motion, maybe in your mind, you know that it could be circular motion, so it could be clockwise or counterclockwise. But by just naming it a circular doesn't mean that a neural network would understand. So you really have to feed the data. And in this case, we actually have to feed the data with the clockwise. And for open set, we have provided the data where we are holding the board steady, we are just moving it around, or we are actually making a zigzag motion, but we did not actually do, of course, clockwise. So this way, these two sets are kind of different. But what about counterclockwise? So we did not actually put any counterclockwise motion in this set. And this is kind of a trick. And this is something I like user to understand and then give it a try. So since counterclockwise is not part of any of these sets, when we encourage people to try it, they would find, oh, it doesn't work. Or sometime it works, sometime it doesn't work. Or when you compile it once, when you're doing counterclockwise, it is detected as a circular clockwise, and sometimes it doesn't. And this is where I really like people to figure it out, how they would actually take more data sets in the next iteration so that they can fix the difference is from the expectation in what the neural network does. So if user really wanted to be clockwise only, then they need to capture more data with the counterclockwise and put it into the open set. Or if they want both of these to be detected as a target classifier, then they may also actually generate two classes. One is a circular clockwise, one is a circular counterclockwise. So with these kind of options, we would see that how you can actually improve the model as the time goes. One note of caution here is that we recommend to use Z in front of the open set. So alphabetically open set is placed as the last classifier. So when you go into the NDP chip, it is treated differently because we need to actually treat the open set differently than the other classifiers. Okay. So now you have got the raw data. You might be interested in looking at it, whether it is a good set of data or not. So in the audio application, you had only one channel of data, which is audio data. Whereas when you are looking the sensor data, it comes with the 6 axes. So by clicking in the browser, you can actually look at these waveforms, and you can see that the data is taken for longer period, whereas this is the gray box is showing a tensor. There is a box here. It says a scale 16-bit to 8 bits, and we recommend not to check it, so leave it unchecked. That's how this actually takes the right default values. Okay, so let's move on. So as I mentioned earlier, that the choice of this 1800 millisecond was kind of important. So here is kind of the math. The sampling rate is 100 hertz, which means that in 1 second, you would actually get 100 samples. And then if it was 1.8 second, which means that you multiply 1.8 by 100, you get 180 samples. But then you realize that there are actually 6 axes there. So you multiply by 6, and you would get 1080 features. And 1080 is divisible by 6 and is divisible by 4, which means that this is a good size of the tensor, and rest of the algorithm would work when it's casted in the hardware. So this is the NDP 101, which actually has a 4-layer of neural networks, and these ones are already coded in the Edge Impulse Studio. So you can see that all these layers are actually predefined. And then it also shows that there are 2 classes. One is circular clockwise motion, and the one is open set. And then you need to do is start training. Okay. So once you understood the tensor size, once you understood how you'll be generating the data from one long sequence and then generating more of these ones from that long sequence, you can actually proceed. Let me go back, and one thing I forgot to mention, which is not shown here, but let's say that in one session, you wanted to capture the circular motion data. And when you started, you might, let's say, hesitated, or you just waited for a second or so. So by the time you go and start the circular motion, there may be some time where the data has not settled yet. So before you actually put that data for the training, you should discard that set of data. You can do that using some kind of a Python algorithm, etc., or program. When the data goes, it should be really the whole data should be for that particular type of motion. Yeah. So this program is already kind of compiled, and you can actually download. So when you're downloading, you would find that there is the bin file is generated with _sensor, and so does the sim package. And this is kind of a specific for the sensor because there are a few things we have to change in the board so that the sensor is actually up and running. In that case, the idea here is that it should actually be having a slightly different name for the bin file, so there's no confusion, and that's why this _sensor is kept here. The building process is the same. It takes 5 to 10 minutes, and you can actually and then downloads, and then if you have a Windows, for example, you would be clicking on flash_windows.bat, and then it would download the model just like the way it used to do before. So now that's taking us to doing the testing on the board. So let's see how that goes. Strange. My link is here, it's not showing. Anyways, so you load the model. Now, if you leave the USB cable connected to it, you might find that your movement is somewhat restricted. And that's one of the key thing when you are working with sensors, that you have to make sure that when you're capturing the data and when you're testing it, the conditions are mimicking the real product. So if you have the wire hanging, then it might actually restrict your movement, and it may not actually capture the data the way you intend. So my recommendation is that at that time, you probably have to use lithium polymer battery. And since the vibrations and other things kind of depend on the packaging and then how board is secured, you may not be interested in actually making a 3D printed model of the gadget you want to make. So the vibrations, etc., are actually part of the training. So yeah, once you download the data, you have to reset the board, and the LED would glow red and then green, and then it would be ready for inferencing. Then you can actually make a counterclockwise motion with a typical radius of about a foot. And don't go too fast, don't go too slow when you're testing this model. Just at the normal speed, which is about 1 second for one turn. And after you have moved it for 1 to 2 circles, you would see the red LED would glow red. Sorry, RGB LEDs would glow red. One thing to note is that by default, the posterior filters are such that it would not trigger the same classifier over and over when you are continue to do that kind of motion. And that is done for good reason, because every time NDP chip actually asserts the interrupt, the host has to wake up. And you don't really want to be waking up the host over and over. So in that case, we only generate like one interrupt. So if you want to give it a try again, then you probably want to wait for a minute or a few seconds. So the open set classifier is triggered, and then you can test it again for the circular motion. So we kept the data very small, which is just a 5 minute of data. And this is strictly done so that we actually give people kind of the starting point. And from that starting point, they would see how many false acceptors are there and how good the recognition is or not for the target sets. And as the time goes, we expect people to enrich the data more. And that can be done quite easily by collecting more data while you are deploying it. And then by choosing the right thresholds, you can actually trigger more often while you're collecting the data. And then after doing some sanitization, you can throw those signal tensors back into the training set and see how the performance is improving. So the real emphasis is really that this project or this workshop actually takes you through the journey, and we give you a starting point, and then after that we expect that you can do a lot more experimentation and learn on this type of project. Yeah, Aurelien, any other question?
Yeah, actually, we had a question from Joseph about what type of sensors you have on the board, actually, and what other sensors are compatible with it.
Okay, so TinyML Board is designed with onboard IMU sensor. So it's a 6-axis Bosch sensor. If somebody wants to add any other sensor, then it has to be connected through our GPIOs. And then the data first goes into the SAMD21, which is a host processor. And over there, you can actually do some pre-processing if you like, and then make a tensor. And then you can actually send the signal to the SPI. So yes, it is possible that you can actually use any other sensor. And all the communication and the setting up the sensor has to be done between the SAMD21 and the sensor. And then we would actually show you how you can actually put data directly into NDP chip. That's not something part of this tutorial, but that's something is doable, and we can help you.
Okay, thank you, Atul.
Okay, so now I have given kind of the flow, how things are, and let me switch the screen so that I can walk you through what we just talked about on the actual project, Edge Impulse project. Unfortunately, the way it is set up, I think it's a Zoom thing where it does not allow to go back and forth between the different windows. Okay. So this is the project, and this is where you would actually click on clone. So I'm not cloning it right now. It would not allow me to change the program, but I just wanted to show a couple of things. So let's go with the data acquisition. If you click on this filter icon, you would see there are two classifiers, circular, clockwise, and open set. And if you click in any of these ones, you actually get to see what they are. So in this case, this is an open set. Now let me unselect open set, and that should be circular. So if I click it here, that's the data which is fed into the neural network. That's may not make a whole lot of sense, This is yet another example. So that's how you can actually look at your data. You notice that these sets are pretty small sets. They are not actually extensive, but each of these ones actually is 10 seconds long. Let's see if this one is also 10 seconds long. So they're about, let's say, 10 seconds long. And each tensor is 1.8 seconds. So if we just divide it, 10 divided by 1.8, we only get 5.5. So maybe we just get 5 tensors. But that's not true, because that means that all these things are actually taken one after another one. So you know that we can generate a lot of these tensors by moving the window slowly by 60 milliseconds. And if we do that math, 10 seconds divided by 0.06 is about 160 tensors. So each of these 10 seconds of captured data can generate like about 160 tensors. So for certain cases where there is no start and stop of the event, and it's like a vibration and things like that, this method would work. But if you have, let's say, something like you want to flick your wrist and you want to detect that, in this case, this is actually one event. And in that case, you don't want to be saving much longer. You save before and after maybe 2 seconds, and then align the data so that your motion is kind of captured and it looks similar between the tensors. So the next step actually is the impulse design. Okay, and this is yeah, it's grayed out for me. So let me see if I can just give me.
While you are switching, there is a question from Swapnil that I think I can answer as well.
Okay, please.
Asking about the sound data sampling, because like the IMU data sampling, as you said, is like limited to 100 hertz.
Yeah.
But for audio, for the microphone, I think it's like 16 kilohertz, right?
That's correct. So I hope you can see the screen. So it is the same project, and if I go into create impulse, if I remove this block, so let me delete it first, and then I want to say add a processing block. So you get multiple choices. So in this case, you'd be selecting IMU Syntiant, and then you would see these axes, and it kind of says Syntiant IMU. Similarly, here in this step, if I remove it and then say add a learning block, and you use Keras in this case, and based on the context, it kind of knows that this is IME application, so it would be choosing this, and then you would actually say save impulse. One thing to note here is that the data goes directly from the sensors to the neural network without any major processing. For example, there is no FFT is taken. The data actually is time domain data kind of comes in and goes into neural network without any FFT kind of convergence. There is, however, one thing to note is that the neural network only takes 8-bit of data, whereas sensor generates a 16-bit of data. So by default, we discard the lower 8 bits and we take the top 8 bits of data. And that's how this kind of a setup is there. If you have a different need where you want to actually take different portion of the data, or if you want to do some kind of a pre-processing, then that's something which we have to work together. So reach us out for that type of application. So yeah, I was saying that we have to convert 16 bits to 8 bits. That's already done. And so we recommend not to check this box right now. And other than that, I think everything else is what we have done before. Even for our audio application, just choose number of training cycles and leave these things by default. They are actually pretty good. In this application, we really don't have the augmentation for the noise because it's not like an audio application. If we find that certain ways the data should be augmented, then that has to be done prior to uploading the data. Because that kind of data augmentation you would do for other situations, for example, audio may not apply here. And over here, you would see the description of the neural network. Dropout layers are there to improve the resilience. And you can click on the Start Training button. You see that the accuracy is quite high. There are two good reasons for that. One, data is small, and this is not a very challenging application. So that's kind of takes all the things I thought people should know before they give it a try. Aurelien, any other question, or you want to jump in?
Hi. In this short video, we will test TinyML Board where we have loaded a circular motion model. So let me power this thing up. So as it is,
can you hear it or not?
First, RGB LED would glow red, then green, and now it is ready for testing. Now, if I move it in a random orientation, it does not glow red. And now I started putting in a circular motion, and you can see it goes into red.
So that was a very quick demo when I was actually moving into random motion, the LEDs would not change. When I moved into a circular motion, LED was turning red. Unfortunately, the movement was pretty fast and you can only see the red light kind of in the surrounding. You cannot actually see it as it was stationary. But in the end, you saw that. So that's how it's supposed to work. So do we have any other question? Yeah, looks like there's one more question.
Yeah, Justin was asking about, I think on the video you just shared, like if you have any model file for the 3D print enclosure.
So do I have what?
Like, do you have like any 3D printing enclosure file for like the demo you were showing on the video? Like the casing on the video, is it something public or it's something you've made yourself?
Yes. So yeah, so as I said earlier, that when you are actually working with the motion, you have to be careful with the proper securing the board because the motion sensor is on the board. And if board is kind of dangling in the air, then it would actually pick a lot of other irrelevant kind of motion. So it is good to make something with a 3D. So yeah, so please reach us out on the Syntiant forum. And then I would actually share the model files. They are done in Tinkercad. And then I would share actually the original files, and then you can modify it so that you can secure the board elsewhere.
Yeah, I think that's all for the questions.
Okay, so if there's no more question, then I can actually conclude this session. But feel free to reach us out, and this is going to be very interesting use case. And I would be really interested to see how people would use TinyML Board for motion applications.
Thank you, Atul, and thank you, everyone.